number of factors determine community resilience. Everything from the natural hazard all the way through to a number of planning or the extent that the community has planned and prepared for the natural hazard. This session is focusing on the built environment, and several speakers are going to come up and talk about work that's been done recently by peer researchers to evaluate the performance of existing structures, to develop retrofit techniques and new design techniques that will enhance building performance and thus reduce community vulnerability, and also to develop new design procedures for bridge structures that achieve both improved performance as well as rapid construction. I've asked each speaker to also spend a minute or two thinking about where research addressing the built environment will go in the future as peer and the natural hazard engineering community seek to enhance community resilience further. We have 4 speakers, Professors Moehle, Roeder, Mahin, and Eberhard, speaking, as I said, about a range of topics. So thank you for giving them your attention for the next, unfortunately we got less time than everybody else, so for the next 80 minutes or so. Our first speaker is Professor Jack Moehle from UC Berkeley, who to some extent needs no introduction, but I will introduce him as the first director of peer and my PhD advisor.
All right. I love seeing this first slide because I don't quite know what the name of this mountain is anymore. Greg Derline suggested that maybe it's the new Trump Tower. Okay, great. Believe it or not, it's about 20 years since the idea of peer as an earthquake center sort of came into reality. And hard to believe for me that it was really 20 years ago. And when peer was first formed, we didn't really know what direction we were going to go. You have to realize it was in the aftermath of, shortly after the 1994 Northridge earthquake, the 1995 Kobe earthquake, and everybody was buzzing about near-fault ground motions and the effects of earthquakes on large cities. There was this other idea floating around about performance-based earthquake engineering. And we really couldn't decide whether we were going up and down or left and right with one topic or the other. And during the first year, we settled on the idea that performance-based earthquake engineering should really be the focus for the peer center. And that we would maintain some of the ideas related to near-fault ground motion and cities and so forth as test beds. And so the very first test bed we had, one of the first ones was this very famous Holiday Inn building, which had been damaged in the 1994 Northridge earthquake. It's not so easy to see, but maybe we can point, but there was damage to columns across this story. Famously at the time, many engineers, experts in the field, analyzed this building with the recorded ground motions, with known material properties, with known structural drawings and so forth. Nobody could calculate that the failures would occur in the story where they did occur. But that was 20 years ago, okay? And here we are 20 years later. We'll talk about that a bit later. This became one of our big focus areas, was non-ductile concrete buildings. At the time, most of the analyses were fairly capable of representing a sideway kind of collapse. We do have those types of collapses occasionally in older concrete buildings, but it's only occasionally. Most of the failures and collapses end up being associated with a shear failure in vertical carrying elements, columns usually, which then is followed by an axial load failure, which precipitates then a cascading failure, sometimes stopped in motion like shown on the photograph on the right, sometimes not. And so we were very interested in understanding these behaviors. 20 years ago, we didn't have really a very good idea about how these things work. And we're still working a little on it, but we've learned a lot in the intervening time. We came to know that in columns of certain aspect ratios and reinforcement quantities, the failure was quite complicated, and there were interactions among many different behavior modes. For example, if flexural yielding started at one point in the testing of a column, that would trigger changes within the column section that would reduce shear strength and precipitate a shear failure at some point further along. As the shear strength degraded, the appearance was that as strength degraded down essentially to zero, an axial failure could be triggered. And this was an early observation with a few tests, and these kinds of things were pursued through the development of some shear friction models, and there's been a variety of these kinds of things developed over time. This very simple shear friction model is wonderful in the sense that it says that the axial strength is essentially directly proportional to the shear strength provided by the transverse steel. And we'll see that in a moment. Now, this was developed based on very few tests 20 years ago. And of course, we needed to do more testing. And so there were many tests that were carried out under the auspices of Peer. Some were done at Berkeley, some at UCLA. There were eventually column tests that were carried out at Purdue University, at the University of Minnesota as part of the NEAST program. And we had a very strong collaboration with researchers in Japan and in Taiwan, and many other tests were also carried out in those countries. But Peer really got that whole program going in those countries as well. And after many, many tests, here's a sampling of some of the data. And this is that shear friction model result shown on the left axis, the vertical axis, the axial load divided by essentially the shear strength provided by the transverse steel, an equation all the structural engineers know. But there's how the data relate to that. We had to ask the question, how does biaxial loading affect the answer? It does, as one would expect. There's a more rapid degradation in axial force carrying capacity under bidirectional loading. And these kinds of ideas have been adopted into ASCE 41 and elsewhere and are in widespread use today. We also had questions about the behavior of beam column joints. Can beam column failures trigger the failure of a building? Of course they can. If, as in the left figure, if the shear strength of the joints is lost, the columns lose their moment carrying strength. You can't transfer moment through a joint that has no concrete left. And so joint failure transforms a strong column frame into a weak column frame. And then of course we know a weak column frame can develop a mechanism and fail, as shown on the left. There's also the question though whether or not the failure of a joint itself can trigger axial failure without the step of having a soft story. And so this was a question that was of great interest also as we embarked on our studies within Peer as the research results developed. There were tests on beam column joints that were done at University of Utah. Chris Panelides is here. Others were done at University of Washington. And then there were also some tests at Berkeley. The tests at Washington, some of the results are shown here, were very interesting in that they exposed the sensitivity of joint strength to what was going on in the beams. As beam yielding occurred, strain penetration in the yielding bars that penetrated into the joints reduced the strength of the joint or the deformation capacity of the joint. We found that there was a very strong interaction between the beam yielding and what was going on inside the joints. We won't talk about it today, just mention it. There also was an effort at that time at the University of Washington to begin recording very carefully what were the various damaged states associated with different levels of performance. And we can see here, well, this is what the joint looks like at yielding. Here it is when there's measurable residual cracks. Here's longitudinal bar buckling and so forth. And these kinds of studies, to me, were the start of developing fragility data and repair cost data that became an essential part of the ATC 58 project. And a lot of the data were really initiated in peer studies on older concrete joints and then columns and many other things. There also were very important models for behavior of joints that were developed. At Berkeley, Professor Mosalam and I had a couple students working on exterior corner joints, a variety of interesting findings. One of the big questions that we had at the time was whether or not the failure of a corner joint, as in the building on the right, can the failure of that joint trigger axial failure? And so data were collected from the tests we ran as well as many other tests. And the blue diamonds are instances in which axial failure was noticed. And the green triangles are instances in which we didn't see any signs of axial failure. There seems like there's a safe zone for performance. And then there's an area with high axial force and high drift for which axial failure seems certainly a triggering phenomenon. Now, all of these things that were done within peer were always done with the purpose of developing an analytical model. It's okay to test something, but only if you develop models for use in practice, only if you develop simulation capabilities that can be used to extend the results. And that was always a part of all the work that we did in the non-ductile concrete building domain. Wasim Ghanou, who is here from UT Austin, was one of our graduate students at the time. He went on to UT Austin and developed some models. Kurt Hazelton, Greg Deerlang, Ken Elwood, others developed other models for the behavior of columns. I just showed this as one example where in this example there's a line element between the end regions of a column. There is a lump plasticity zone, the spirally spring for flexural yielding, and there's an interaction between that spirally flexural spring and the shear behavior. And this can be extended out to also have an interaction between those different springs and an axial failure model, and those kinds of things were also implemented. Now, the purpose for developing these things was so that we could understand better how buildings would respond. To really develop that understanding, we also in peer carried out a series of shaking table tests. One example was a series of two column frames. There were a dozen of those. And then we did the other case that had a dozen columns but only one frame. To understand what some of the dynamics was, there were other tests that were run at NCRE looking at multiple columns. We're looking at beam column joints that failed. This allowed us means for testing the analytical models that were developed. And here's an example of a test in a simple two-column frame that sustains shear and axial failure. Can we model that? Can we identify when those things occur? And we gained confidence as we worked with these models that we were able to predict certain things, not everything. You know, once axial failure gets triggered, it's very hard to follow through in these very lightly reinforced cases. But having some experience enabled us to extend ideas out further. Abby Leal, Kurt Hazelton were graduate students in peer at the time, working with Greg Deerlang. One of the very interesting studies was to look at the relative safety of older concrete buildings versus, at the time, newer concrete buildings. And we can see here the predominant yielding mechanisms that developed. And then in this case, the different fragility relations for newer buildings and older buildings. And a simple observation from these is that there are cases where the older buildings are something like 10, 20 times more risky than the new buildings, all right? And so these studies were very important for understanding, for quantifying the risk at hand. And additional studies have been carried out to look at how details of the frames affect that calculated risk. And this is an example where on one axis we've got the relative column to beam strength ratio. On the other axis is how strong is the frame relative to the elastic demand. And this is a case where it's a flexure critical column. And what's plotted here is the probability of collapse as a function of these parameters. As we move more toward shear critical columns, the fragility goes up and up and up. And this beautiful colored balloon-like thing is not only beautiful and colorful, but it tells us something about what are the parameters that most indicate a risky building. And it's these kinds of things that can be used in the future. Laura asked, what are the future needs? And some of the future needs are to take the models and do more work on those models to understand better what are the most risky combinations, what building types are the most hazardous, how can we develop better hazardous models going forward. We heard the need for this morning. In Peer, we also, somebody turned me on. Oh, turned me back on, okay.
That was 50 minutes.
Okay. We also did a very interesting thing as part of a grand challenge project is we went down to Los Angeles and we counted buildings. And then we did studies of what the projected losses would be. And for better or worse, the LA Times got wind of this. It made me almost like a movie set. It made for me a most dangerous year, wondering when I would get sued. But eventually it resulted in an ordinance being passed. That and other things contributed, came together and helped develop an ordinance for LA that I feel Peer deserves some of the credit for. And we've also, as a center and as researchers and as graduates, been involved in many different activities that are taking what we've learned in this center and expanding it outward. And I think that's a really important part of making a difference with the Earthquake Center. So then and now, this is the old Holiday Inn building. I don't think we yet could calculate exactly where the failures occur, but it doesn't matter because the new one is retrofitted. And we have some new challenge to deal with there. Those of you who came in this building, I assume read the signage on the way in. This building is located in a seismically active area. The fault is like 20 yards away from here. And in the event of an earthquake, serious injury or property damage may occur. So this is a concrete building. It's a type that we haven't studied so much yet, and I think there's plenty of room for continued research in this broader area of reinforced concrete construction. So we can go to places like LA and San Francisco and continue to make a difference in seismic safety for these kinds of buildings. Thank you.
Are there any questions?
That looks like no. Oh, okay.
So it occurs to me as you're speaking, do you think that we will get to the point where we can model Van Nuys Holiday in its old state before all of those buildings get torn down and rebuilt?
So yeah, great question. Will we get to that state? I think there's enough variability in the ground motion, how the ground motion gets into a building, and enough variability in the innards of every building that's out there that we may never be able to predict exactly what happened. But I think we're close enough now where we can understand what the relative risk is for buildings of that type with that kind of detail, so that we can go out and make more educated calculations or guesses on what the fragilities of the inventory looks like. And I think once we can do that in a better way, we can more confidently pick out the kinds of buildings that are the highest risk. Tomorrow, remind me, Bill Holmes will be here tomorrow talking about that ATC 78 project, where there's a team using these results, trying to sort out what are the conditions in existing concrete buildings that make them the most collapse prone. And I think that's the big challenge ahead of us. How for a $5,000 analysis can we go to a building and give it a thumbs up or a thumbs down?
We'll look forward to that tomorrow.
Thanks, Laura.
So our next speaker probably needs no introduction. Has certainly won any number of awards honoring the work that he has done with respect to steel structures. And today, Professor Roeder from the University of Washington will be talking about evaluation procedures and new design procedures for brace frames, assuming that he can find his file on the Macintosh computer. It's my fault, I touched it. Where is Is that but it's Microsoft sent me? Yeah, right. Oh, it's putting it there. Okay, so that's, but this is not. It's not like that. It's not showing.
That's not one.
Right. Oh.
That's not one.
Oh, now we're back into it. That's all. So actually, it's a presentation right now. This is totally reversed from what we were expecting.
Well, good afternoon. I'm going to talk about brace frames today. Talk about the evaluation of older brace frames and design of new brace frames. Brace frames are a structural system that have been around for many, many years. There are brace frames in service today that have been in service for almost 100 years. But brace frames are a relatively new system for seismic design. This seems rather strange to say because brace frames have been designed for seismic loads for many, many years. But up until about 1990, brace frames were designed for seismic loads in much the same way as they would be designed for wind load or almost any other kind of application. There was no consideration given to their ductility. There was no consideration given to their inelastic deformation capacity. In the 1980s, the U.S.-Japan program performed a test program on steel structures in Tsukuba, and one of these tests was a concentrically braced frame. And the results of that test, combined with research that was done probably over the several years at the University of Michigan, really started the first thinking about designing brace frames, truly designing them for seismic design, considering where yielding is going to occur, considering their behavior that would occur. And I think that that's really when we really started to do serious seismic design for brace frames in the United States. But because of that, I think you'll find that in general, it's a less well understood system by structural engineers. It's a system that structural engineers have a love-hate or a fear mechanism with. On the one hand, they like the structural system because it's economical, it can be quick, it can be a very good structural design. It appears to be a very simple design because you're looking at a truss system. But unfortunately, many structural engineers don't really understand what they're expecting the structural system to do seismically, and this has caused real problems. As a consequence of this, there has been fairly significant research on brace frames in the last 10 to 15 years that I think hopefully is trying to help better understand the performance of brace frames, improve the seismic design of brace frames, to better understand the performance of brace frames that we built before any consideration of seismic design, and to do a retrofit of this. And that's pretty much what I'm going to try to talk about today. The work that I'm going to focus on today has primarily been 3 National Science Foundations projects that have been performed since, I guess, 2003, continuing on to today. The research that's been done on these projects has been done at 4 major institutions. In the upper left, you see our lab at the University of Washington in Seattle, and we've tested more than 50 single-story, single-bay brace frames in our laboratory under a range of, with the different braces and a wide range of different connections to evaluate their seismic performance. On the upper right, you'll see the Mass laboratory in Minnesota. And in this laboratory, 2-story brace frames were tested, and these were 3-dimensional type frames, and they were tested under bidirectional type loading at that university. And these simulated, really more accurately simulated the boundary conditions for brace frames. On the bottom left, you will see a frame at the Encre laboratory in Taiwan. This laboratory has tested 12, not 8 as I've shown here, 12 multi-story, 2- or 3-story brace frames with concrete slabs under a range of different seismic applications with different types of braces. And on the bottom right, you see some 2-story frames that were tested here at the laboratory at Berkeley. I think there were 6 of those tests, if my count is correct. These were 2-story frames, they did not have slabs. So the focus I'm going to be talking about today is going to be the results of these tests. There were several other research projects on brace frames in the last 12 years, and they would include some research that was done at the University of Buffalo, Georgia Tech University, and the Miki Test Laboratory in Japan. My focus is going to be the results of these works. Now, I've made presentations of these. We made one presentation a few years ago that was over 4 hours. I don't think you want to sit here for 4 hours today. I'm told you could have 15 minutes. So rather than going through a lot of talk about the researchers doing, I'm going to try to focus on key results that I think are the results of this, and things that I think that are significant achievements from this particular work. First, and I think thing we really need to think about is when people think in terms of brace frames and when people think in terms of structural design, they think about designing member by member. And I think if you think about designing a brace frame member by member, you're probably not going to do a very good job. With brace frames, you've got to think of much more about the system, because the member acts with the rest of the structure. You have to think about the brace, you have to think how its connection and the rest of the framing members. Because in brace frames, buckling is our major consideration, but there's a lot of inelastic deformation in the gusset plate connections that are connecting the brace to the regular framing, and then the beam columns themselves. Secondly, I think you have to recognize that inelastic deformation of the brace is a primary inelastic behavior. Buckling is not the end of the world. Buckling is a yield mechanism. It's a way to deform the structure. It dissipates energy. Fracture of the brace is a thing that's ultimately going to occur. But brace fracture does not imply structural fracture. And I think these are two perceptions that I think people have about brace frames that tend to lead them astray in their thinking. So in doing this, we've come up with what we think are some recommendations for new construction, which are quite useful and quite valuable. One decision is that currently when you design the connections for the expected capacity of the brace. And then when you design the welds joining the gusset plate to the brace, most people use the uniform force method for that expected force. What I'd like to show to you is that is not going to give you good performance. It's going to result in very, very limited ductility, and it's very likely to end up with weld fractures such as you see right here. If we're going to be designing brace frame gusset plates to get good elastic performance, we got to design the welds so that the welds joining the gusset plates to the beam and the column are strong enough to develop the full inelastic deformation capacity of the gusset plate. Because the gusset plate will yield. It will go through inelastic deformation. I don't care how big you make it, that deformation is going to occur. And the consequence, we've got to design the welds to be big enough to develop that particular gusset plate. Another thing that we've developed is the clearance models. Because in buckling there's a great deal of out-of-plane deformation of the brace, this causes the end rotation on the gusset plate. And you've got to consider that. Historically, we've used the 2T sub P linear clearance model. And there's nothing wrong with this model, except that it does tend to sometimes lead to fairly large gusset plates. And these large gusset plates tend to be controlled by buckling because you have to bring the brace back quite severely. So we've proposed some better models, we think, for evaluating this, which is more reflective of the way they actually behave. We propose for corner gusset plates, we propose that it use an elliptical clearance model as shown on the left here, because this reflects the pattern of yielding that you typically see in these gusset plates. And for mid-span gussets, we propose a 6T sub P linear clearance at that location. We've proposed these because they allow you to bring the brace back further, which means the buckling no longer controls the design of the gusset plate, which means you're using a thinner, more deformable gusset plate, which means you can use smaller welds when you weld the gusset plate, and it actually increases the elastic deformation capacity of the system. We also propose a balanced design procedure for these gusset plates. This balanced design procedure is a capacity-based design procedure in much the same way as we normally use. With this procedure, however, we like to use a increased yielding in the gusset plate, and we like to use a relaxed block shear criteria. And the reason for this is, if you have a little bit more yielding in the gusset plate, you get a lot less damage to the beams and the columns and other structural members. And so we think that this improves the performance. It actually increases the inelastic deformation capacity of the brace, an average of 46%. So what we're really proposing today is we're proposing something that is a sequence of behaviors. We expect that the first thing that's probably going to occur is brace yielding, brace buckling and brace yielding. Buckling typically occurs first. Shortly after that, we expect that there's going to be some yielding in the gusset plate. There will ultimately be some yielding in the beam of the column. But ultimately, we expect that the outcome is going to be brace fracture. But brace fracture does not mean collapse. The frame still has significant inelastic deformation capacity after this. What's that? We like to also say that engineers feel that being conservative is better. And that when we design something, the forces that we design for are the minimum design forces. If we design for something more and make it bigger, that's better. And I'd like to say in brace frames, that's not true. Here we have a comparison of two frames. The frames are identical, the same beams, the same columns. The difference is, on the top one, we designed the gusset plates so that they satisfied our capacity design requirements, but they were closely designed. They were not overly strong. On the bottom one, we have a very, very conservative design for these gusset plates. You see the behavior. The one on the top has much more inelastic deformation capacity than the one on the bottom. The one on the bottom failed in exactly the same way. They both had brace fracture, but they fractured much, much earlier because we were being very, very conservative with the gusset plate and thinking we were being better when in actual fact we were making the situation worse. There's another strong feeling that seems to perpetuate us today, and that is that buckling restraint braces are the best thing since mother and apple pie. And I want to say that buckling restraint braces are good, but they're not perfect. Here's 4 photographs of buckling restraint brace frame connections. The top one, you see the buckling restraint brace has moved out of plane. It's not because the buckling restraint brace behaved badly. It's a problem because the yielding that occurred because of the buckling restraint brace in the beam and the column means that we're no longer able to restrain that particular connection. In the other 3 photographs, we see fractures of the beams and the columns because of these strain hardening effects. Buckling restraint braces are a hardening system. They increase the force significantly with increasing deformation. This causes increased yieldings of the beams and the columns and the problems associated with this. More recently, we've been doing research on older pre-1990 brace frames. To start with this, we looked at an extensive number of design drawings of older buildings, mainly from California, but also from Washington, Oregon, and some other parts of the United States. In doing this, we see a lot of deficiencies. We have figures of what these look like. I'm not going to focus on all of these. I picked out several of these deficiencies to like to talk about. One deficiency is that almost all of those older brace frames are chevrons. We don't use chevrons hardly at all today because of the strength requirements in the beams. Okay? We find that many of those have understrength gussets with no end rotation clearance. We find that the welds are deficient. They're deficient because they are not demand-critical welds, and they're deficient because the welds themselves are undersized. I think you'll find they commonly use HSS braces, and the HSS braces are very slender compared to today's requirements. They have a wide range of bolted and welded connections. Many of these we have tested in our research. What I'd like to say about these older brace frames is some of these systems aren't that bad. Some of them are almost as good as what we'll be designing today, maybe better. Some of them are very, very bad, and some of them are very, very serious problems. Here I think you'll see one that is actually pretty good. It's not bad at all. On the left you'll see an SCBF bolted connection that's designed by today's criteria. On the right you'll see an older connection, and you'll see that the older connection gets as much, if not more, ductility than we get out of our new system. Why is this? Well, because the older system had deficient gusset plates so that it was yielding in the gusset plates and was getting bolt hole elongation. And that bolt hole elongation really contributed a lot of inelastic deformation capacity to the system. Today, we design our bolts very, very conservatively, and you don't get this. So that in effect, we were fracturing our brace much more earlier in these systems. As I pointed out, not all deficiencies are equally critical. Some seem to have bigger consequences than others. End rotation doesn't seem to be as big a problem. Understrength gusset plates doesn't seem to be a bit of a problem. Bolt hole elongation, which occurs with these weaker gussets, is often a good thing. Net section, we find, is not a real problem in many cases. It requires a very, very special set of conditions to occur. D over T ratios, on the other hand, are a very serious problem. If you have a very slender brace, it fails very, very quickly. Here you see that in one of these connections right here, which had relatively limited deformation capacity with a very, very slender brace, a brace that's commonly used in some of these older buildings. We looked at methods for possibly fixing that. One method is to fill the thing up with concrete, with concrete to make a tube. We did this. In this test, I think you'll find that it's done very, very well. However, it's not a perfect situation. Here on the left, you'll see a second test. I think this test was done by Barbara Simpson here at the University of California, Berkeley, where you did not good performance. The reason for the difference between the two, on the test on the left, the concrete fill engaged the connection. The one on the right, the concrete fill stopped short of the connection. Since the concrete fill gauged the connection, it made the brace stronger, it attracted larger forces and larger strains, causing the brace to fail more quickly. So we think this concrete build tube concept is a good concept for possibly improving the performance of these slender braces, but you really have to keep the concrete well clear of the connection. Weld fracture is another relatively serious problem. It didn't seem to be quite as serious as we expected, largely because I think the gusset plates were almost invariably also weak and not protected them. We tried a potential economical retrofit for those with weld overlays. Weld overlays were tried in the Sac Steel project with not very good success. But we found that weld overlays have actually been fairly beneficial with these gusset plates. We designed the weld overlays with demand-critical welds, and we sized them to develop the plastic capacity of the gusset plate. Final thing I want to mention is that we performed tests at the Entry Laboratory where the chevron beam was much weaker than what we require today. We find in some of these old designs, these beams are about 1/8 of what they need to be. This beam was only 40% of what it needed to be. We find that actually the performance is pretty good. In fact, here is a comparison of an SCBF frame on the left, which had the same brace, a slightly bigger column, and tested at the same facility. And in many respects, we find the weaker beam looks almost as good as the other systems. Well, we've also done quite a lot of work in developing nonlinear models to predict our performance, focusing on the connection, focusing on brace fracture. At my time, we compared all of these tests with the experimental results. And here's a comparison showing the stiffness, the comparison of the prediction of brace fracture. Using this information, we use this to estimate what we expect the performance of brace frames to be. Here is a comparison of the expected behaviors that we would expect of a brace, subject to a 2 and 50% acceleration record, if on the left a 3-story building, on the middle a 9-story building, and the right a 20-story building. And using information of this type, we think could be beneficial in helping us do further improvements in brace frame design. So I think there have been some significant developments in brace frame research. I think there are a lot of things we've learned. I think there are ways we can continue to improve the performance. I think there's a considerable way we can have to go. In any case, I think we need to think in terms of system performance. We need to think in terms of yield mechanism and failure modes. And we need to be a bit more sophisticated in our thinking of brace frames. And I've overtalked too long, but this is a photograph of the University of Washington campus, which I always use to tell me it's time to shut up. Which, is very much a member related. But I don't think it requires all that much thinking. It's doing a program where you have do statements and if statements and if. And you need to think about, well, if I have this, I need to condition my response on two or three things rather than just a single variable. But I think we have to do a better job, or I don't think we're going to have the full benefit of what we can get out of this.
Any other questions? Please. I think there's a microphone somewhere, but.
Similar question. Is there then a conflict between system-based thinking and capacity design?
I don't think there's a conflict between what we're saying capacity-based design. I think it's just a modification of the way you apply capacity-based design. I mean, I think right now the capacity-based design looks at things in this way. Our recommendations really do not change that in any way. We're looking at the same basic capacity-based conditions. We like to apply them differently and think about them differently. think capacity-based design tends to make you want to be very conservative in everything else. But, you know, think about that. I mean, you can all easily think of many where it's easy to get to extremes like that.
Well, the idea there is you pick your mechanism in advance and you design everything else to stay elastic, to develop that one mechanism.
Well, designing everything, why do you design everything? What seems to me, you design everything else to be strong enough so that it doesn't have problems.
Yeah.
Why does it have to be elastic? You know, you don't want it to have problems. And that's, we're very definitely trying to do that type of behavior. I think that if you can readily see that, well, for example, in this building here, if you said, okay, I want the columns to have no shear problems, which I don't know if they do or not. But anyway, you can put a ton of shear reinforcement. You can put 3 or 4 times as much shear reinforcement as you need. Does that help you? It might actually make the situation worse because it may attract forces. It may cause things that you don't expect. So we think you should design it to be good enough, strong enough, but no more. Sorry.
Thank you.
Thank you.
So if one looks around Berkeley, Seattle, maybe not Berkeley, San Francisco, Oakland, Seattle, LA, it seems like the only thing that's being built is the mega tall building. There must be 12, 13 cranes in Seattle, and I'm sure it's the same elsewhere. So clearly, thinking about the performance of these tall buildings in these high seismic regions is important to community resilience. Professor Mahin, the previous director up here, is going to talk about work that's been done by peer researchers addressing tall buildings.
There we go. Well, anyway, it's good to see you again, and we have a little bit more audience than we did this morning, so that's great to see everyone. What I thought I'd do today was to talk a little bit about tall buildings, and I'm not going to talk so much about the research or research results, but I think this was intended to maybe help us focus on some of the philosophical issues with regard to resilience and the seismic performance we'd like to have in structures to get some of the discussions going later in the meeting. This is related to tall buildings. It's a topic that I've been working on for most of my career in one form or another, and I've come back to in the last 4 or 5 years in some significance. Part of that reason is that this is a building not in Berkeley, but on the border of Berkeley. It's, I think, it was the tallest reinforced concrete moment frame building in the United States in 1984, and I live right there. Which suggests that after the next earthquake, there may be something like 1,200 angry lawyers and one really upset structural engineering professor. In any event, that was what was the tallest building, and now in California there are taller buildings. But if you look around the world, one of the questions is what constitutes a tall building? So you don't have to go very far, and people from Shanghai who are here with us will recognize this building. So my tall building, which is 30 stories, is 1/3 of the size of something that would be a relatively mid-level tall building in much of the rest of the world. So tall is, a relative term, and most likely we will get up to these heights at some point. So again, what can we learn from the lower buildings to go to super tall buildings as well? This is a little bit more complicated, and what I'm trying to look at here is extrapolating what we know from a 3 or 5 story building to a 30 story building to a 90 story building to a 120 story building, and not thinking that anything has changed here. So this is a couple of buildings. One is in Los Angeles. It's just finishing construction, and the other one is just coming up out of the ground in San Francisco, and these are around 300 meters tall. If you look at them, they are very substantial, But when I was a student, everyone said you should have a dual system with a backup system, and they should have some redundancy. But a lot of these systems now have very little redundancy. There's a single core in the middle of it, and if there is anything else, there may be an outrigger system. But we've worked our way into thinking that that's a good thing. It wasn't a good thing 30 years ago, or 20 years ago, 15 years ago, but now it's a good thing. So I agree with everybody, it's a good thing. But the next earthquake, we'll see whether or not we are right or wrong. These buildings are also becoming taller, but they're not necessarily becoming wider. And so if you look at the building on the right-hand side, which is the Wilshire Grand Hotel in San Francisco, in Los Angeles, it's very narrow. You can see the shading of the shear wall there, and it has then a series of outriggers at 3 different levels in it. And it's so narrow that it was very hard to keep it from tipping over. And so you can see at the bottom of it, there's a little foot that sticks out. The shear wall goes down and turns left. And that's just to keep the building so that it is able to develop the moments that go into the foundation region. So these buildings are starting to get up taller and taller, but they're relatively regular. And if you look around the world, there's very few really regular buildings. And so if you look at the trends in design, these are new buildings that have just been constructed by, I think both of them by American engineers, and architects rather. And they're sort of twisted and a little bit bent. Okay? So you think, well, that's just an architect being an architect. But engineers did this. And the reason for that is if you look at wind tunnel tests, you'll find that a square building is about the worst thing that you can build in floor plan. That on the far left-hand side of this graph, on the right-hand side of the graph thing, is sort of what a square building would do. The one that is next to it that is even worse had some openings at the top of it. But if you go along a horizontal line through what the point is on the left, where it has an axis label of 1, it's everything compared to that. If you come across that graph, what you'll see is there's a round building, there's a triangular building, which is about one of the worst. And you come over, and in the middle, you'll see some buildings which are square and just twisted. And the more you twist the building, the lower the floor level accelerations will be, the lower the moments will be, lower the shears will be. And so if someone was trying to optimize a tall building, you would make them look like a wood screw, something like that. Have them twist as much as possible like that to reduce vortex shedding. All right, and so as a result, looking at this very carefully, you would find that a round structure that twists somehow is going to have about the best behavior, and that's why you end up with this building on the right-hand side here. Okay, so the architects look at architectural magazines. Somebody in San Francisco is going to look and see these buildings. One of them is designed by an architectural firm in San Francisco. And they will just start building these and assume that engineers just will extrapolate one more time and build something that will perform well in an earthquake. And so one of the things to see in anticipation, not necessarily wait for the next earthquake, is to see whether or not we believe that we can extrapolate to these kinds of situations. Now, architects do some really strange things that aren't recommended by engineers. And this is a building currently under design in Los Angeles. And there are no columns whatsoever in the building that run vertically. There's no columns on the inside of the building at all. And so this is just an exoskeleton with just this twisted stuff that you see on the outside. Moreover, the shear wall that holds the building up is this white thing on the outside of the building, about 50 feet away from the center of the structure. Okay, so architects are architects, and they just design it. That's what you end up with. And now an engineer is trying to use ASCE 41 to design this. Okay, none of those connections have ever been tested. None of them satisfy any building code requirement, and they're trying now to seismically isolate it so they can say it's elastic, therefore it doesn't have to be ductile or tested whatsoever. Okay? So, these things are happening to us, and after the next earthquake, this may just be perfect. The other ones might be perfect, but we're going to see some surprises, I would believe, and there's an opportunity to look at that. So almost all tall buildings are somehow going to violate today the prescriptive requirements of ASCE 7 or ICBO or something like that, and they're going to be based on performance-based design, and as a result, ASCE 41 and the Peer Tall Building Initiative guidelines are oftentimes used. In doing that, Jack and the group that had developed a tall building did an excellent job. They're in the process of starting to revise or review and then revise as necessary the guidelines now for peer. But out of that, you end up with a Vision 2000 peer methodology, ASCE 41 little chart here that suggests that you can do a matrix that relates to the seismic performance, severity or rarity of the earthquake motion, and that would be done by basically something here where you would look at the performance you would expect for a very rare event or moderate event and for a very frequently occurring event and assign those. And so the design process that's outlined in the Tall Building Initiative is you basically design the building as if it were code compliant and consider what exceptions there might be there and ignore some of them and take account of the other ones as appropriate. Then you would do a elastic analysis for a service level event to make sure it doesn't yield too early and cause damage under frequent events, and then do a nonlinear analysis of the structure for a larger event that would be rare, and you want to make sure that the structure satisfies the requirements of the building code for the code level performance-based earthquake engineering. So one of the unknown things in this graph is basically the type of building that you would have. This is sort of a basic objective for the yellow, but there's hazardous buildings, essential buildings, and safety critical structures. But one of the philosophical questions is a tall building just an ordinary building? And so and I think Peer had a workshop and sort of agreed at that point that these buildings were in risk category 2. But if you look at ASCE 7, it says for risk category 3 that this is a building with potential to cause substantial economic impact or mass disruption of the day-to-day civilian life in the event of a failure. And so the question is, if you have a building that has 5,000 people in it, is that going to be a massive disruption of ordinary day-to-day life, especially when people who live in those types of structures are all lawyers or IT guys who then have 3 or 4 lawyers that work for them, and there's nothing good that can come from that. All right? So one of the things then that comes up is that the CALBO, the California Building Officials Organization, has put out an interim guideline that suggests that if you have a building that is red tagged, any building within that height of that building, or in some cases 1.5 times the height of the building, is also automatically red tagged. And you see that in New Zealand, you saw that in Napa, that buildings that had no damage whatsoever were close to another building and they were red tagged. So if I have a tall building, then anything within 330 meters of the base of the building is also red tagged, which then gives you the notion that if you have some tall building like this, you're going to red tag a fair amount of real estate. If you have a city that has 5 of these in it, you're going to wipe out, or red tag most of the city in some cases. So the question is whether that's rational or not. I think Professor Mosalam is looking at the potential for collapse and when things actually go over like a big sequoia tree or come straight down, like Jack was saying, is a subject of potential research. The other thing is that if you look at the building codes today, it has a nice chapter in ASCE 713. Chapter 13 is for non-structural elements. But if you look at it, it says that you would design a structure for the non-structural elements for the case where you have the design level earthquake. There's no design consideration whatsoever in the code for the MCE level event. So if you do have an MCE level event, this is perfectly acceptable behavior, I would believe, by my reading of the code. for the behavior of the structure. So there's a question then, if you have a tall building like this, which then, under the sea level event, might actually structurally behave quite well, and you have this kind of behavior, we also potentially have to look at that. So I think there's an issue of what we want these structures to do, and then how do we get them to do it. And so in that regard, I think there's an opportunity for engineers and researchers to do more work on figuring out how to build resilient structures. This would be basically the needed capacity design, locate the damage where you would like it to be, make everything else behave well, make the plastic hinges durable and easy to repair, make them easy to make damage easy to find and quick to repair, but also then to come up with structural systems that will reduce the relative displacements of the structure, the accelerations of the structure, and if possible have some self-centering mechanism that would reduce permanent displacements. And so we've all seen, work that's looking at adding viscous dampers and energy dissipating devices of various sorts or other, and using seismic isolation. For tall buildings, people have used outriggers, outriggers with dampers in them, and various combinations of very clever things involving outriggers. But one of the things is, if I live in my apartment, and assuming it had a shear wall in it, it does not, and I came home at night and I walked up to the front door, there would be an elevator, and that elevator would be the shear wall, and I would note that the shear wall just had lots of cracks in it that I might be able to put my hand through. And so I'm not going to go into that building. It's going to be red tagged. And so the upper part of the building, outside the plastic hinge region, may just be perfect. So we're building the entrance to a building in the plastic hinge region, which I think is just perfect. But we'll see after the next earthquake. So the question is, can we avoid some of these kinds of problems? And so one way of doing that, we have looked, many of you have looked at this for smaller buildings, is to have some type of recentering system. And the shear wall, there's no reason why you have to have them be continuous monolithic construction. You can just have something sit on the ground, armor it in some fashion, post-tension it if you need to get this recentering properties operating. You can also then put in viscous dampers or buckling restraint braces for the reinforcement in there. And if this worked perfectly, which nobody I know has tested, one could see whether or not you could have a plastic hinge that is mechanical, but is pretty much indistinguishable after an earthquake happens. That just opens up and closes like that. And the same thing can be done for these outriggers. There's buckling restraint braces and outriggers, but one could easily do outriggers that recenter in the same way. Take a shear wall that's vertical. Deerline has done tests on that. I've done a few tests on that. You just turn them 90 degrees and call them outriggers in the tall building, something like that. And then lastly, I'm doing a lot of work myself on seismic isolation of tall buildings. This isn't particularly tall. But the purpose of this slide is that blue line in here. This is a test that Carrie Ryan from Reno and I did a few years ago. But basically, the table's moving back and forth about a meter, and the building relative to the blue line moves about 8 inches at a frequency of maybe 6 seconds or something like that. So in terms of the horizontal motion, it's just like being a little boat and you're moving back and forth, whereas if you stood on the ground, it's shaking pretty violently like that. And so if you look at the animation of the structural analysis, it looks like the building is going back and forth because the ground's not moving in most animations you would do, but it's really the ground is moving back and forth and the building is staying stationary. So as far as the occupants go, I think the isolation might be a little bit better. I left out a slide. I was going to show some examples of some of the analyses that we've done, but basically the studies we've done is showing that, as one might expect, the isolation systems could reduce the displacement demands and drift demands in the structure by perhaps a factor of reduce them to a third or less of what they would be for a fixed base case, reduce the accelerations by a factor of 4 or 5 in some cases, and the bearing demands might be fairly large, a meter, meter and a half, 2 meters, like that, depending on what kind of ground motion you have. So anyway, in conclusion, I think tall buildings become a way of focusing on some really expensive and high-value piece of real estate that makes some of the studies that we do for performance-based design and resilience studies economically feasible to do. We'll do hundreds of trial analyses of floor systems to minimize the cost of a tall building. So performance-based design is not something that is particularly unusual, and most of them are being designed by performance-based design methods anyway. But if we do that, then I think there's an importance of bringing into the consideration the business interruption losses that might be associated with this, and the large consequences of residual displacements that might dominate the economic losses that we would have, both in terms of the individual building and adjacent buildings. There's an opportunity to look at different kinds of structural systems that may be new, that would have less damage, and to utilize new and innovative concepts and devices, and to take advantage of high-performance computing. And then when we get into tall buildings, this gives us the chance to do multi-hazard analysis. You get the tall building, you have to worry about wind, almost no matter where you are. And so we have to start looking at the interaction between wind and earthquake-related issues in terms of human comfort for one-year windstorm, non-structural damage for wind and for earthquake, which may be controlled by different things, and then to extend the peer methodology of E58 to not just earthquakes, but what are the fragility functions we would use for partitions? We would go from the EDPs to DOs, and what is the losses that we would associate with, we talked about gravel, breaking windows, rain coming into your building is a different thing than you would have in an earthquake or interstory drift. So we need some loss functions there as well. So anyway, that's it. Just some food for thought, and hope there may be some room for some research and some collaboration on this. Thank you.
With the objective of only going over our allotted time by a little bit, I think we're going to hold questions, Professor Mahin, until
That's my thoughts.
after the session. And I'll introduce our final speaker. Professor Eberhard is going to be talking about another critical component of building infrastructure, bridge systems, but only if I can figure out how to do this. So I think I got it. It's fine.
Well, good afternoon, and thank you for staying here till at the end of the day. It's always a privilege to speak to all of you. It's also a privilege to follow Steve Mahin. But Steve, I need to tell you something. You freaked me out. Because I live in Seattle where we have tall buildings and there's new ones going up. And we have long period motions coming in the future that last for a very long time. And if you tell me things are not good in San Francisco, then I'm even more worried about Seattle. But anyway, so I can now worry about that in addition to other things in life. So thank you. Okay, so let me get started. By acknowledging the many contributors to this presentation, I can go through a lot of projects and talk about rapid construction. About 10 years ago, there was almost no work done on rapid construction in seismic zones. Over the last 5 years or so, there's tons of work going on. I'm only going to cover some highlights, and I apologize if I missed your project. And I certainly can't go through and talk about exactly who funded what, because there's so much collaboration going on among the agencies, among the researchers, that who knows what idea came up. So I'm going to thank everyone way in the beginning for all the great work. On the right-hand side, I just have a list of people who submitted slides to me. And so thank you, thank you, thank you. And for those of you who I missed, I apologize. Okay, so the first question, of course, is why you want to accelerate bridge construction in the first place. And the main thing people think about is a traffic jam here. I'm not suggesting that's due to bridge construction, but certainly bridge construction hurts your traffic congestion, and it happens in the entire construction process. But I just want to point out there are other reasons you might want to accelerate construction. If you're in an environmentally sensitive area, you're going across a river, you have salmon runs in Seattle, you have trout runs in the mountains. Also, you have a very short window for construction. If you look at Alaska, you live in the mountains here or somewhere else, you have a short construction season. So a lot of the reasons you want to get in there and get out as fast as possible. So really, the speed of construction shows up in many different ways. Okay, so first of all, we certainly want to accelerate construction, but the good news is that if we're going to develop new systems, we can have some other performance goals beyond just going fast. And certainly we like to limit damage. We like to have our bridge go back to the original place where it started. If we're going to start doing some kind of performance-based evaluation and design, we should be able to predict how it's going to behave. And finally, nothing is free. You have to work with economics. And my sense is the only way that economics work for these new systems is if one considers economics in a broadly construed sense. It's not just the cost of materials and labor at the beginning, it's the cost of maintenance, it's the cost of construction disruption, it's the cost of disruption after an earthquake. And it becomes that cost issue and the benefit issue pretty sticky with it. Okay, so the main contribution that Pierre's been doing in the rapid construction area has been through the bridge column program, focusing on the idea of dissipating energies at the ends of columns. And as in most structures, the issues are usually mainly about the connections. And so we developed a series of new systems of 4 different teams working in parallel, and then one reference column with which to compare these new systems. And this is led by Steve and Matt and Vesna at Berkeley. They have a standard column using Caltrans criteria that's flexurally dominant for it to compare. There are 4 systems. The one we did at Bridge in Washington had a hinge that was hollow, shell at the bottom, which with a hybrid fiber-reinforced concrete developed by Claudia Ostertag and her colleagues. It used to be more ductile at the base. It has pre-tensioning to get the column back in place. And the idea is to use pre-tensioning rather than post-tensioning because pre-tensioning occurs in a lab, in a factory, whereas post-tensioning slows down the construction process. There was a column that had HYFRC, a solid block at the bottom, designed by, at Berkeley, by Mario Spanagiotto, and again, Caltrans was involved in that. In that case, they had post-tensioning in the column moving back to place. And also, they wanted to make sure they had the interface occurring right at the base where you would have the opening and closing cracks, so there were headed bars which essentially would pound on each other as we went back and forth. There was a system out of San Diego, Jose Restrepo and his colleagues. They did initial work funded by FHWA, but they followed up with a system funded by Pierre, and that had such a tube inside a tube, which comes in quite quickly, and then it's grounded at the bottom interface. And then again, that's creating just almost a rocking behavior at the bottom. And then finally, because we're doing these 3 new systems and the reference column, it gave us the opportunity to test the effect of a retrofit or repair, which would be probably a better way to look at it. Where Mr. Mosalam and his colleagues looked at the idea of putting fiber wrap on the column. So if we start looking at the response, I have a video from San Diego, which works on this computer. And so this is actually a design level motion, but it's a second design level motion. So it's been already subjected to 1, and it's now going through its second earthquake at the same potential level. And I mean this with all respect to Jose, it's kind of a boring video, right? Basically, at the design level, you have a joint opening and closing, it's going back to place. There's not a whole lot of nonlinear behavior going on. So at the design level, you're doing just fine. And frankly, all the systems tend to do just fine at design level. And so this slide's too complicated to see from the back, but essentially it shows the 4 new systems on top. It shows a conventional column on the bottom. It shows the damage at the end of the design level. And you can look really carefully and basically see how thick the markers were when we marked cracks right after the earthquake. But in the design level, all the 4 new systems work. But frankly, the conventional reinforced concrete column does just fine at design level as well. The cracks are a little bit open, but I don't think there's any question that that bridge would be serviceable right after the earthquake. As you go beyond design, you increase is about double design. You get more and more damage. And there you start seeing the problems and the advantages of various systems. At the bottom of the pictures, there's actually bar buckling and bar fracture coming up. That conventional column, clearly you have problems with that bridge. In the one at University of Washington, I'll fess up to the fact that our column didn't do all that great. We had an HYFRC at the bottom, but we did ensure we had a hinge opening at the interface. And believe it or not, it opened up about 6-8 inches above the interface. Anyone who can explain to me why the moment of the cantilever is larger, 8 inches up than the bottom of the cantilever, then please let me know. But once that crack had formed, it then rocked. And it rocked quite well, but it rocked about 8 inches above the top, so it didn't look very nice. Both the dual shell and the hybrid reinforced concrete column did better in sense of concentrating deformation. And most of the deformation occurred to, most of the errors, most of the problems occurred right at that interface. Either spalling the concrete in the HYFRC column, or spalling and kind of messing up with the grout in the San Diego column. Okay? Residual displacements was another performance goal. In black, there I show all the 5 systems, in red I show all the 5 systems, what's going on during design. Well, frankly, none of the systems have a lot of elastic action. All of them go pretty much back to where they started off. But again, if you go to that earthquake 7, the much larger earthquake, you can see there's differences among the systems start to appear. And so, looking quickly at those, the main difference is the top 4, even at the larger earthquake, come back to the original position. The bottom one's conventional column. That one has large residual displacements. In fact, it's leaning. You can see it visually at the end of that motion. So in residual displacements, you have kind of the same thing we had with damage, which is at the design level, things really aren't that different. But at higher design levels, things are quite different. We've since gone to University of Washington, a new system. We decided we're definitely going to have that interface be the walking interface. And so we've armored that cross-section in a precast column, but a precast column that has this boot or the shell, this armor at the base, and we're darn sure it's going to rock right at the base, and it's going to rock on that steel shell. So you can think of it as a boot, you can think of it as a tiny, tiny concrete filled tube, but it's a precast column with pretensioning in it to bring it back to its position. And back in 2005, we had done some tests that had nothing to do with rapid construction, but they were tests of a reinforced concrete bridge at the University of Nevada, Reno. And this is at twice the design level. This is at, really? Okay. This is not at twice design level. This is a cool video too. You know what? It's late in the afternoon. So, bridge goes back and forth. Concrete falls. People go, wow, that's a lot of damage. Okay, that's that video. I wish I could juggle, but I don't know how to juggle, so I have to do comedy instead. Okay, this one, let's see if it works. Otherwise, I can give you the quick version. Okay. Bridge goes back and forth. The columns essentially remain rigid. It just rocks back and forth, rocks back and forth. At the end, it comes back to exactly where it started, and there's no damage whatsoever you can see in the column. Hey, it got better than the video. He's a video. Okay? But the differences are enormous. Now, there are a lot of systems have been developed outside this program. I want to go through them relatively quickly and just give you a sense of what else is available out there. Professor Roeder, Lehman, and their colleagues at Washington, and a lot of other people have worked on concrete-filled tubes. There, essentially, you bring a concrete tube, a steel tube to the site, you lay it flat, brace it, you put grout to hold it in place, fill it up with concrete, grout a precast beam on top of it, and then you go through and continue your bridge. They looked a lot at the capacity. In the capacities, you can see that on the upper figure, around 3 or 4% start getting some buckling at the base. It still works fine. And around 7 or 8%, you start getting some ripping and tearing of the tube. But that's just the capacity side. You also have the demand side, right? And one of the nice things with a concrete-filled tube is that because we have that concrete on the outside, you're not going to have a lot of reduction in steel on the outside. You're not going to have all that reduction in stiffness. So using FEMA 695 motions, those scales and all that, looking at the design level, Max Stevens, one of their PhD students, looked at essentially the drift demands for reinforced concrete column and equivalent CFT column. And the bottom line of all those analyses is on average, you get a 1.4% drift versus 1.8% drift for the CFT column as opposed to reinforced concrete. And that makes sense because you suppress a lot of the mechanisms that reduce the stiffness of a reinforced concrete column. Again, it's outside of peer, but some good work that's been done at University of Nevada, Reno. These are 3 projects that were led by Saeed Zaidi, but I know he has collaborators on all these. This one is a column, it's a bridge that has 3 different systems in it. It has concrete-filled tubes, both precast on one side and also cast-in-filled, cast-in-place on the other end. In the middle, there's some segmental segments that have CFRP wrapped around them. And then at the top, 2 of the vents also have pipe pins. And all of these things are kind of methods to increase the performance. More recently, we're looking also kind of traditional duct and bar work, in this case using a UHPC. And on the right-hand side, it's really pulling out all the stops on the materials. There's a precast footing. It has SMA bars coming out of it. And then on top of that is an ECC precast element that's put on the bars to give you ductility. And that system has a very good performance, of course using some pretty fancy materials to get there. Okay, so that rush through everything, I think we can pull some pretty clear lessons out of those results. The first one is certainly we've shown you can get much better performance with a system that can be built quickly. And no matter what, no matter how you study it, the key to rapid construction is always some kind of prefabrication. To get reduced residual displacements, everyone ends up using pre-stressing of one sort or another. Either it's pre-stressing like we're doing, pre-tensioning like we prefer, or post-tensioning like most systems have done. And then it turns out that really to get that good predictable performance, it makes sense to concentrate all your deformations in one location and make sure that that location can take those large deformations. And all the systems that have been successful, not only on these and some others, have combined those 3 principles. So I think in terms of peer, we've got to figure out where we want to go beyond this. And certainly one of the issues now is one has to prioritize designs and decide really what do you want to run with, and go 1 or 2 or 3. And that'd be great if peer researchers sat down and made that decision, except that no one would really care. You only can make these kind of decisions by broadening that discussion. And that discussion is going to have bridge owners, contractors, designers, people who come in and say, well, you can design that, you can come up with that system, but I'm not going to build it. Well, we want to have things that are built. That discussion definitely has to go beyond just the research community, and that's a good next step. Certainly, one test is not a design spec. One test is not confidence that you can build 100 bridges out of this. So there's going to be some specimen refinements. There's no research team that doesn't want to go back and make a little change to what they did before. We certainly should be looking at some larger scale tests, and if possible, some system tests on some of the nicer facilities that are available. Of course, in the long run, as part of PEER, we want to incorporate that into the PBB framework. And I'd argue the work we've done so far is kind of easy stuff, which is getting a ductile connection to work, something that's relatively easy to put together. The hard stuff is really trying to figure out when's the best time to use it and how do you quantify the benefits and costs of using that system. As I said way in the beginning, the benefits and costs involve construction, congestion, avoidance by doing something quickly. Gosh, do you have to do a whole system analysis every time you want to replace a bridge with rapid construction? How about maintenance? How about downtime? How about repair? All this kind of stuff goes into it. And as we speak to stakeholders, probably new concerns will come up. And on one hand, we want to be able to quantify those. But I also think it's really important to be able to simplify the approach by which you handle those. So one gives you different ways of doing it. One way is to categorize routes. You know, this is a level 1 route, this is a level 2 route, this is a level 3 route. On level 1, we'll have this level of performance. We're going to assume that delay costs are by this many vehicles or something like that. I don't think it makes sense to go through and look at every individual bridge, unless it's a Bay Bridge or something like that, and try to work out these costs. And then finally, of course, if we want people to use them, we have to take all this research and translate it to design tools and guidelines. It's a relatively new area, rapid construction in seismic zones, but it's exciting because I think there's a great future for using things coming up and trying to avoid construction where we can, just where we can. Thank you.
Again, I'm sorry, I think we're going to leave questions for tomorrow's sessions. I would encourage you to come tomorrow. There are some breakout sessions that are going to talk about research needs and the future of research with respect to bridge construction, new buildings, and evaluation and retrofit of existing buildings. So thank you very much again to all 4 of our speakers. And my profuse apologies to Professor Mosalam, who is our incoming peer director, who is now going to close off today's session. Not quite, I guess there's a closure session afterwards.
Well, good afternoon. Been sitting for too long, but I promise I won't take too much of your time. I don't have slides, so I had a lot of notes today. So there was a very good talks, and Greg was questioning his wisdom speaking after 3 great speakers. Look at me, I'm speaking after all these great speakers. So my name is Khalid Mosalam. I'm a professor of structural engineering at UC Berkeley, and I assumed my new position as peer director 4 weeks ago. So I'm very excited about this job. It's a very important job because the center is very important. It's very relevant, and it means a lot to all of us. I started my career when the center started. I came to Berkeley in '97, and the center started in '96. So I feel like I benefited a lot from this center. But as excited as I am, I feel the burden that this will be a difficult job, simply because I have to follow the footsteps of Steve Mahin. And Steve has a lot of knowledge and experience, and he works very hard and has a very clear vision of what should be done, and that sets the bar very high. So I'm aware of that, but I am relying on the generosity of Steve. He has been very generous with me since I started in Berkeley. He shared a lot of all these attributes with me in addition to time, and I am relying on that. I am fortunate to have two of the previous director of the center as my colleagues, and I'm not very shy to go ask them questions, and I hope they keep their door open for me. But turning to Steve, we heard today a lot of accomplishments that took place under Steve's direction, and I would like just to highlight a few of them as a summary of what we heard. So there was a significant continuation of the performance-based earthquake engineering methodology, what Steve called the peer DNA. I like that very much, so I will make use of it more and more. And it's enabling technologies that continue to develop under his direction, in particular OpenSeas, databases, the whole family of NGA, East, West, 1, 2, 3, subduction. So this is all great. Also the liquefaction database, and OpenFresco that we haven't heard much about, but Steve single-handedly with his group and collaborators have developed this important technology as well that we all benefited from. We also heard about all this extension of peer performance-based engineering in general, how it's extending into the areas of tsunami, possibly fire after earthquake. We heard the performance-based earthquake engineering applications that span from tall building initiative to bridges, whether they for rapid construction or for resilient design. Also applications in lifelines from power generation to distribution systems. Also Steve enlightened us about some important future directions towards resilient infrastructure systems. I would say you coined the name Resilient California. The first time I heard it from you, so I don't think anybody, I think you have the originality of that. You kept important niche sites as members of peer active, so they were successful in having NERI awards, so I would say that's an important accomplishment. And you were able to do all that with a very lean operation, very capable staff. So I can go on and on, but it's getting late. So please join me in thanking Steve for his leadership, for all the accomplishments peer managed to achieve under this leadership. Thank you, Steve. So to summarize, in addition to all these accomplishments that are attributed to Steve and his team, we also heard a lot of important things from all the talks we enjoyed today. They show the breadth and the depth of the peer research or or research that's relevant to peer mission. And I just want to highlight also some of these things we heard. We had a great overview of resilience of our built environment and how performance-based engineering framework can be expanded to include this important and highly visible concept, water resiliency and or sustainability is very popular these days, and we seem to be heading in the right direction with that. We learned what does resiliency mean from engineering, ecological, and also from transformative, especially after an extreme event points of view. We learned the 6 steps involving planning guide that NIST is investing in for community resiliency. We learned important issues related to interdependencies with concrete examples like the SPUR project. We learned about research challenges of peer performance earthquake engineering and how this can be extended to resiliency concept. For example, involving the process of recovery and going from a single building to a community. And then we had a whole set of presentations that are of peer-focused research, and the themes of these were geohazard. We heard quite a bit from NGA to NGL to LEAP. Very interesting framework that can benefit not just the liquefaction studies, but it can be emulated, whether we want to develop accurate constitutive modeling, how you actually marry experiments to analysis in this seamless way. We heard also in-depth presentation about an important topic of structure, soil, foundation interaction. And then we had the second theme that had to do with tsunami, and it shows how peer is expanding its emphasis in that important direction. So we learned about performance-based tsunami engineering, tsunami bridge simulation and design, tsunami end-to-end analysis, very interesting comparison between probabilistic seismic hazard analysis and probabilistic tsunami hazard analysis. We have seen in-depth coverage of tsunami intensity measures, so we can determine, for example, the hydrodynamic forces, inundation depth, and tsunami hazard and casualties. Agent-based modeling, very interesting concept. And how we go from source to site, and then how we look at this hazard and its effect on different type of structure. And we have seen all the interesting development in computation, expansion of open seas capabilities, and then seeing also open foam and how it can conduct computational fluid dynamics. And the third theme we saw today is related to the built environment. Jack gave a nice review of the past test beds that dates back to the early years of peer, and then significant research on non-ductile reinforced concrete buildings, followed by a great overview of braced frames. I learned that local damage in the different members doesn't mean global collapse, so that is very interesting to know. I learned that braced frames should not be designed member by member, they should be designed as system. And then we saw a fascinating presentation from Steve about tall buildings with great looking but somewhat scary structures that are being built. We have seen interesting things related to, I'm not sure, that's not my phone, that's something ringing here. Somebody left his phone here, that's ringing. That's not mine. I don't know, I'll turn it off. And then we saw interesting discussion about the red tagging and the influence area that can be probably offset. Oh, turn this thing off. Somebody is very good. Maybe somebody tell me to shut up. And how this can be avoided with interventions, whether it's rocking system or recentering or isolation. And then the last theme, or the last topic in this theme, was the rapid construction of bridges, where several tests took place within the peer activities. Some envisioned modern systems that minimize the damage or possibly eliminate the damage. And we learned that quick construction, not necessarily inversely proportional to good performance. You can actually achieve both. That's interesting. So that's quickly a summary of my notes. I have a lot more, but I think I will stop here. So I have maybe 2 more minutes, just a word about what we will do tomorrow, and then a few announcements that Grace asked me to share with you. So about tomorrow, I'm really looking forward to the discussion in the breakout session. I'm looking forward to the report, different reports by the moderators. This will be important for the peer administration to prioritize the research agenda for the coming years. So please work hard on providing that guidance to us because it will be very important. Few announcements. The poster session will start in about 32 minutes. And that will be, if you just go through this door and just go straight through the corridor, will be to your left. That will be in the Great Hall. There is about 2 dozens of posters of research that's of relevance to the peer activities and mission. So that will be from 5:30 until 7:30. The business and industry partner dinner, that's by invitation, will start at 6:30. I want to remind you of the peer survey, either the online or the hard copy. It says it will close at 7 p.m. So please fill this out. It's important for us. Cheryl and Sahar have worked very hard on this, and we thank them for that. So we would like to provide them with as much feedback as we can. And finally, please leave your, at the end of the day, your name tag at the reception desk, the registration desk, because we will need that tomorrow to check you in when you come in the morning. With that, please enjoy the rest of the evening, the poster session, and those who will go for the dinner. And I'm looking forward to seeing you again tomorrow. So we can learn more about the future direction that peers should be heading towards. Thank you very much.